I wait for introducing for a moment. Okay, so I suppose we may start with the next talk. The next speaker is Daniel Méry. I hope I pronounce in the right way. Speaking about Beth Semantics and labeled Deduction for Intuitionistic Sentential Calculus with Identity. So Daniel, you may start. Okay, I see you are starting. I suppose this will be pre-recorded talk, so now I will turn off my video.
So, hello everyone. This talk is about Beth Semantics and label deduction for intuitionistic sentential calculus with identity, and it is joint work with Didi Gelmish and Marta Gavek. So, a few words about sentential calculus with identity, SCI for short. It was introduced by Bloom and Suszko in 1972 as an extension of classical logic. As you know, in classical logic, only two situations are possible, truth and falsity. But in SCI, there can be more than two different situations. Therefore, SCI has an identity connective which allows us to witness the fact that two propositions denote the same situation. For example, two logically equivalent formulas might not be considered identical. For instance, even if a formula A is logically equivalent to a formula B, A and B might not have the same set of proofs. So now from the point of view of deduction in SCI, there are already existing proof systems, a Raziowa-Sikorsky proof system for SCI by Kolinska and Pilarek, Sequent calculi in Negri style for SCI by Schlebowski, but those calculi do not have the subformula property, and so they does not yield a decidability procedure. Let's mention that SCI can also be studied in the context of intuitionistic logic. And then we have ISCI. For ISCIs, we also have an algebraic semantics and a cryptic semantics. And Schlebowski introduced a Hilbert calculus, which is sound and complete with respect to this cryptic semantics. But once again, all those calculi are designed following the Negri and von Plato approach, and they don't have the subformula property, so they cannot yield decision procedures. So decidability is still an open question in ISCI. So our goal in this talk is to study new semantics and new calculi for ISCI. Our contributions are a new class of models for ISCI, which we call Beth Semantics, which are sound and complete, and which have a regularity property which is important for decidability. We also provide a new labeled Sequent calculus, which is sound and complete with respect to our Beth Semantics, but which is not analytic. And then another labeled Sequent calculus, which is sound and complete, but which also admits cut elimination, which terminates, from which we can derive the decidability of ISCI. So now let's move to ISCI. We start with a countable set of propositional letters, and then we have the set of formulas F, which is given by the following grammar. So these are the clauses for intuitionistic logic as usual, and we have the identity connective, which is called also equations. Identities are also called equations. And if we want to axiomatize ISCI, we need to take any suitable set of axioms for intuitionistic logic, and then we add the four axioms for identity. One which says that identity is reflexive, and if A equals B, then not A equals not B. If A equals B, then B implies A. And if A equals B and C equals D, then A times C equals B times D, where time is any of the binary connectives of ISCI. With this, we can do Hilbert proofs. For example, we can show that the identity connective is symmetric. For example, A equals to B implies B equals to A. for this, we need to apply modus ponens several times and use axioms from intuitionistic logic and from identity. Okay, ISCI has already existed semantics, but the most notable one is the cryptosemantics introduced by Schlibowski. Cryptosemantics has a very simple and natural interpretation of disjunction as M satisfies A or B if M satisfies A or M satisfies B, which is what you would expect from disjunction. In this paper and in this talk, we introduce a Beth semantics. So we have a more complicated clause for interpreting disjunction, which is borrowed from the topological models of intuitionistic logic, but in a more algebraic context of distributive bounded lattices. But while we lose the simple interpretation of disjunction, we gain a key property of the forcing relation, which is regularity, which is what enables us to show decidability. So let's take a look at Beth semantics for ISCI. We start with a set of worlds, which contains two worlds, omega and pi, which are respectively the least and greatest element with respect to an ordering relation. A Beth frame is simply a bounded distributive lattice. And we then enrich this Beth frame to obtain a premodel by adding a valuation function from worlds to propositional letters and equations. This valuation is such that the valuation of pi contains all propositional letters and all equations. Then we have Kripke monotonicity, and we have conditions that reflect the axioms for identity. With the valuation, we derive a forcing relation, which is the smallest relation on the worlds and formulas such that M forces P if P is in the valuation of M, as expected. Similarly for equations. The most notable difference with Kripke semantics is that we have a world, pi, which forces inconsistency. And the other distinction is the interpretation of disjunction, which is such that M forces A or B if one can find two worlds, N1 and 2, such that their meet, N1 with N2 is less than M, and N1 forces A, and N2 forces B. A Beth model is then simply a Beth pre-model, which also satisfies the following admissibility condition, which says that if M forces A equals B, then it forces B imply A. We can show that those Beth models are sound by showing that they validate all the axioms of the Hilbert system, but it is more conveniently obtained by the adequacy of a label calculus that we shall show later. If we now turn to the completeness of Beth model, we obtain completeness by construction of a canonical model that relates the denotations of formula to the derivability relation. Since we don't want an algebraic semantics, we don't do the Lindenbaum-Tarski construction, which relies on equivalent classes, but we use an idea of Beth, which relies on theories of formula. The theory of the formula A is simply the set of all formulas B, which can be derived from A. With all those theories, we gather them in a set which is called T, and a theory X can be the image of several distinct formulas, which are then equivalent. And the representative of the witnesses of this theory are gathered in a set which we call min X, which is a set of all formulas AX, which derives all the formula B in the theory. With this, we derive a canonical Beth frame, which is simply the set of theories arranged as a lattice ordered by inclusion, and in which the theory of top and the theory of bottom respectively are the smallest and greatest elements. Then the meet is given by the disjunction of formulas and the theories that they generate. The join is related to conjunction, and inclusion of theories is related to derivability in the Hilbert system. We still need to define a valuation, and we do this as follows, but this definition is a bit complicated, but it can be simplified, and the valuation in the canonical model is simply the theory itself restricted to equations and propositional letters. With all this, we can show that the canonical model is actually a Beth model because it also satisfies the admissibility conditions. And then we show that Beth models for ISCI are complete. If A is valid, then it is provable in the Hilbert system. But more interestingly, we can also show that Beth models satisfy a regularity property. What is a regular Beth model? It is a model in which whenever a world forces a formula A, it also contains a world which is the smallest world, which is called A minimum, that satisfies A. And it's not difficult to see that for all formulas A, the theory generated by A is A minimal in the canonical model. Therefore, we can show that regular Beth models for ISCI are complete. So if a formula is valid in regular Beth models, then they are also provable in the Hilbert system. So we have now shown that if something is valid in arbitrary Beth model, then it is valid, of course, in regular Beth models because they are a subclass. And if they are valid in regular Beth models, then they are provable in the Hilbert system. Now, let's move to the label deduction for ISCI. We first need the notion of labels. Labels simply are finite subsets of natural numbers. A label X is a sublabel of a label Y if X is included in Y. Then we arrange the finite subsets of N into a lattice ordered by set inclusion and in which the join and the meet are given by standard set union and intersection. And we call this the labeling algebra. We have the notion of a labeled formula, which is only a pair Cx with C a formula and X a label. We have the notion of labeled sequent, which is a pair gamma turnstile delta with gamma and delta multisets of labeled formulas. We introduce a specific notation, O of t, which means that t is a subobject of O. For example, if x and y's are labels, then x of y means that y is a sublabel of x. If delta is a set or a multiset of labeled formula, we use the notion x in delta to mean that in delta there is a labeled formula A with label y, and this label y is such that x is included in y. Using this notation, we can define the notion of a connected sequent, which is just a sequent in which all formulas AX occurring in gamma have a label X, which already occurs in delta. Now, our first label calculus is called N1EC. The E is because there are rules with eigenvariable condition, and the C is because the system has a cut rule. The rules of N1EC are designed so as to preserve connectedness from their conclusion to their premise, and also to preserve principal formula in their premise. For example, with our notation, instead of repeating A and B from the conclusion to the premise, we simply write A and B, knowing that it is a subobject of gamma. So, the labeled calculus N1EC contains a cut rule, and here we see that the cut formula C has a label X, which should already occur in delta to maintain connectedness. The system also has axioms, for example, A occurring with X on the right-hand side and with Y on the left-hand side, on the right-hand side, and with X on the left-hand side, provided that X is included in Y, then it is an identity axiom. Similarly for falsity. And more interestingly, we have identity rules. If we look at rule L1, we see that it can introduce in the premise a formula A equals A, which does not appear in the conclusion. Moreover, we have rules like L2 and L3, for which not A equals not B and B implies A are not subformulas of A equal B. So our system does not have the subformula property. Moreover, if we look at A equals B and not A equals not B, it is easy to see that not A equals not B has more connectives than A equals B, so the premise is larger than the conclusion. We also have logical rules, which are they are intended to be. And we have rules with eigenvariable conditions. For example, if I need to expand A or B on the left-hand side with the label X, I must find on the right-hand side a formula C with label Y, such that X is included in Y, which is the side condition. And then I must generate two distinct singleton labels, a new A to extend X and Y in the left premise, and a new B to extend X and Y in the right premise. So we have freshness conditions. Now, with this system, we can, for example, show that the identity connective is symmetric by putting the formula on the right-hand side and starting with a label which is the empty set. Then, applying all the rules of the system, we finally reach axioms, which means that we have a proof of the symmetry of the identity connective. We can show that L1EC is sound. We can also show that all the axioms for identity and for intuitionistic logic are derivable in L1EC, which implies that if something is provable in the Hilbert system, then it is provable in L1EC. And if a formula is valid in the Beth Semantics, then it is provable in L1EC. So we have shown that if something is valid, then it is provable in the Hilbert system, and if it's provable in the Hilbert system, it is provable in L1EC. But as we saw, L1EC is not well suited for termination. So even if we eliminate cut, we would have problems with the rules for identity. So we are going to replace all the rules for identity with only two special rules to obtain a new system, which is called L2EC. We have a right rule, which says that A equals A on the right-hand side is an axiom. And we have another rule on the left-hand side, which means that if A is equal to B at label X, then I can find any formula C with a label Y such that X is included in Y. And I can generate a formula C sigma, which is obtained from C by replacing all occurrences of B with A if the size of A, taken as a number of connectives, is less than or equal to the size of B. Otherwise, the substitution goes in the other way. We can show that L2EC is sound. We can also show that it is complete with respect to the Hilbert system and to the Beth Semantics. And we do this by showing that any proof of L1EC can be turned into a proof of L2EC with the following proof, which is only interesting to notice that the translation requires the use of cut. So even if I start in L1EC with a proof without cut, the translation will introduce cuts. Therefore, we need to go for cut elimination. Cut elimination is quite involved, and it's too complicated to show it in details, but it relies on the notion of a label substitution. If Y is included in X, then in X, U replaces Y by simply discarding Y and making the union with U. Otherwise, X remains unchanged. With this notion of label substitution, I can show that if I have a sequent gamma delta and a proof of it in L2, a proof of height n, then with the same height, I can prove that S in which U replaces C is also provable. And it's really important that C is a singleton set or the empty set. Otherwise, the substitution lemma does not hold. As usual, cut elimination requires more lemmas, and those lemmas are quite standard in the literature. We need to show that weakening is admissible, that all the rules are height-preserving invertible, that contraction is admissible, and that if I have formulas which are never principal for any sequence, which means they are unused, then I can discard them without impairing provability. With all this, we can prove cut elimination, and our proof follows a standard pattern given in Proof and Analysis by Sarah Negri. We define the cut rank of a cut rule by the size of C, and the height of the both premises of the cut. In the base case, when one of the premises has a proof height of 0, we simply directly eliminate the cut. Otherwise, in the inductive step, we move it one step upward, or we replace it with a cut of smaller rank. All the details are in the paper. But now that we have cut elimination, we know that if a formula is provable in L2 with cut, it is also provable in L2 without the cut. But eliminating the cut is not enough to obtain decidability, because right implication and left disjunction requires eigenvariable conditions. So we now fix this by setting a total injective indexing function, which, given a formula A and an index n, maps the pair an to a singleton label denoted IA of n. For example, now when I expand A or B on the left-hand side, instead of generating a new A each time I encounter this formula and a new B, then I will always reuse the same index, which is I1 A or B, meaning it is the index of A, and I2 A or B, meaning that it is the index of B, and those indexes will get reused time and time again each time I encounter A or B. With those rules, which are the liberalized rule for L2, we can prove that if a formula is provable with the eigenvariable condition, it is also provable without the eigenvariable conditions. Of course, we also need to prove that all this remains sound. And the idea to prove that it remains sound is to interpret the unique index semantically by the A minimal world. So let's start with a regular best model. We define a realization to interpret all the labels by actual words in the model. And this realization is a lattice homomorphism, which preserves the order, and for which, if a formula AX occurs in gamma, then the interpretation of X forces A, and if A labeled with X occurs in delta, then the interpretation of X does not force A. The important thing is that all indexes are interpreted by minimal worlds. And if we do this, we can prove that if a world forces A equals B, then it also forces C, where A is replaced by B if it originally forced C. We can also show that if a sequent is an initial sequent, then it's not realizable. And we can show that every proof rule in L2 preserves realizability in regular Beth models. With all this, we can prove that if A is provable in L2 without the eigenvariable condition, then A is valid in regular Beth models, which means that we have completed the circle. If something is provable in L2 without eigenvariable conditions, it is valid. And if it is valid, it is provable in the Hilbert system and all the subsequent systems, which are then equally powerful with respect to derivability. And they are all sound and complete. So now we can move to decidability. L2 is a terminating proof system, and thus ISCI is a decidable logic. How do we prove this? Of course, without eigenvariables, we can only generate finitely many singletons in a derivation. But since labels are finite union of singletons, there can only be finitely many labels in a derivation. Now, if we use the rule for identity, the special rules always replace a formula with a formula which has a size which is less than or equal to the size of the initial formula, and which is built with the same atoms. Since there are finitely many formulas of size n built from the same set of atoms, which is finite, there can only be finitely many subformulas and labels in a derivation, and therefore only finitely many saturated labeled sequence in a derivation. In other words, the proof search space for a formula A in L2 is finite. So, as a conclusion, and for perspectives, we have the following results: a new sound and complete class of regular best models for ISCI. We have proposed two labeled secant calculi, and the second one as the cut elimination property. It doesn't need any form of eigenvariable conditions. It is terminating, and with it, we can prove the decidability of ISCI. In future works, we might look at alternative proofs of completeness for our labeled calculi, which are based on countermodel construction. And we could also look at proof translations between our labeled calculi and the existing secant calculi, which are label-free, especially the systems by Schlebowski. And I think I have finished, so thank you all for listening.
So let us thank the speaker. And any questions?
There is one hand raised.
Yeah, Anupam and then Malena. I saw Anupam first. Please, Anupam.
Hi, Danielle. Thanks for a very, very nice talk. I enjoyed it a lot. So I guess I'll ask the obvious question. So you've got this really nice decidability proof using proof theoretic methods, which is always a lovely thing to see. Can you say something about the complexity of the decidability proof? Can you say something? Well, first the upper bound that comes from your argument, but also do you know if you can match it with a lower bound?
So for the lower bounds, I don't have I don't have a precise idea for the yes, for the lower bound. I think it is NP complete because intuitionistic logic is NP complete, and we are only performing substitutions for equality. But we haven't studied complexity yet from a very formal point of view. But I think it is at least NP complete, and I think it is p-space, in fact.
Sorry, I think I missed a couple of things. So, intuitionistic logic is NP complete. I think you missed.
So intuition is p-space complete. Yes. So ISCI is bound to be at least p-space complete.
P-space hard.
P-space hard. Yes, and yes, p-space hard. But I think that since we only perform substitutions between formulas which are equal, I think it remains p-space hard. It doesn't go higher, but we don't have a proof of this for now. It's only a conjecture.
So maybe just to touch on this a little, is it? Do you get polynomial depth in the proof search space? Because that would give you p-space algorithm for it, right? As long as the lines are polynomially bounded, of course.
Yes, I think that the depth is polynomial.
Okay, so it suggests that maybe you do have a tight result.
Yes.
Okay.
Yeah.
Please.
That's interesting. Thank you.
Okay. Any more questions? I had a question. So you give some intuition about ISCI, and then you introduced a labeled version of it with finite set of natural numbers as labels. Do you have an intuition about the label system, or is it just an intermediate step in your decidability proof?
Yes, the label system is an intermediate step in the decidability proof, but it is an essential step for the decidability proof because the labels are drawn from the Beth semantics, and without the labels from the Beth semantics, which is regular, we cannot reuse the labels while staying sound, while remaining sound. So to have a sound proof system in which we can reuse the constants, we need to go to Beth semantics. There exist label-free systems, but with label-free system, we don't have the subformula property. And if we go for the subformula properties, then we need to add more structure. And in fact, this structure is exactly, for example, deep inference is exactly what is encoded into the labels used as sets of natural numbers. So it was natural to go to the labeled system.
So if a formula is labeled 2, 3, 4, what does it mean?
Sorry.
What could mean? Of course, it depends on some environment, but what could mean labels? So a label set 2, 3, 4.
It means that if you have 2, 3, 4, if 2 is the label which was introduced with A, 2, for example, with formula B, and 3 with formula C, then you have the encoding of a world in the Beth semantics or also in the Kripke semantics at which A, B, and C is forced. So there is a mapping between the natural numbers and the formulas, and between the labels and the worlds in a semantics, which in our case is a Beth semantics.
Okay, I think I get some of the idea. Many thanks again, and okay, I think I'm clapping. Anyway, I thank the speaker again by hand, just to be on the safe side.